Thank you very much. And it's my pleasure, actually, to give a talk here in this wonderful conference. So thanks for having the opportunity to do so. And that's very recent joint work with my colleagues Giovanni Peccati and Yogeshwaran, the first from Luxembourg University and the second from Bangalore. And actually, he will give the next talk. So somehow the talks are connected. I will focus on one part of our recent work and Yogesh on another part. Okay, so what it is all about, before turning to the topic, just to fix some notation here. So all what you need to remember here is that there is a certain phase space X. You can see the pointer, I hope. Okay. And there is a space bold N, which is the space of all counting measures on X with multiplicities, which are locally finite. So there is a certain system, let's say, of bounded sets on which the elements of this bold N are finite. So it could be X could be Rd, or could be the space of convex particles, or could be a space of suitable functions, or whatever. And as usual, we equip this bold N space, the space of all configurations, with sigma field, which makes this evaluation map measurable. So that's just notation. Bold N is the main notation here, and X, state space and space of configurations. Okay, and then as we all know, a point process eta is it's a random element of the space defined over some probability space. And as we all know, a very specific but still very important process is a Poisson process, which has these two fundamental properties. It is completely independent, meaning that the number of points in disjoint sets are independent, and for a fixed set B, the number of points within B has a Poisson distribution. And its distribution is completely characterized by the intensity measure, which is given by this formula, and we denote it in this talk by P sub lambda. And please interrupt me whenever you have a question. Okay, so, but now, here is the first important definition for this talk, which is the definition of a stopping set. So a stopping set as, first of all, it has a certain measurability property, namely the one stated here. I will put it now on my desk better. Which means joint measurability of this mapping of this indicator function as a function of X and of the configuration U. But here is the important property, which is hopefully easy to explain. Namely, maybe I can even make a picture here. So our points are scattered in space. And let's say the stopping set looks like this. Doesn't need to look that simple, but I can only draw simple property pictures here. And there are, of course, many other points in the complement of that. Okay, and now this equation says the following: if I change the points in the complement in an arbitrary manner, so I keep some of the points, I'm adding some new points, okay, and apply this mapping set again, then nothing changes. So set, I should have mentioned this at the very beginning, takes values in the space of all measurable subsets of X, which is this space here. And there are plenty of examples, in particular in stochastic geometry, plenty of examples of stopping sets. And here is a certain notation. This thing here is the restriction of mu to the stopping set. So this thing here. And C is an arbitrary configuration, and restricting it to the complement means I do something in the complement. So that's the stopping set. Okay. Now, a stopping set, when combined with a Poisson process, is a wonderful thing. Namely, we have a spatial Markov property. And let's try to decode this, this equation here. So what does it tell us? It tells us the following. Given the points within the stopping set, so this is the configuration eta restricted to the stopping set, the conditional distribution of the configuration in the complement of the stopping set is that of a Poisson process. And what's the intensity measure of the Poisson process? It's just a restriction of the original intensity measure to the complement. That's true at least if the Poisson process has just a finite number of points in the stopping set, but it can be extended to more general stopping sets, even though this property is for many applications already sufficient. So it's a spatial Markov property, which is well known. Maybe not in this generality, but it's just that it was common wisdom since the 70s or so. Okay. And we will use this Markov property, spatial Markov property a lot. So that's the definition of a stopping set. This is the extension to stopping sets, extension of the Markov property to stopping sets, which can contain infinitely many points. Okay. And now what is the Schramm-Steif inequality? In fact, the Poisson version. What we mean by this? In order to explain it, we need to introduce the notion of a Wiener-Ito integral of order k. So I don't give the explicit definition, just assuming that you have seen it somewhere, I hope. For any k and for any square-integrable function where square integrability refers to the case product of the given intensity measure, we have this object, which is a square-integrable random variable. And later you will see the Keras expansion of a square-integrable random variable. So we fix this notation just for later purposes. What we also fix more or less for the whole talk is a stopping set. And now we say that the function f on n is determined by the stopping set if this simple equation holds. So the value of f at some configuration mu is already determined by the restriction of the configuration mu to the stopping set. In that case, we say that the function is determined by a stopping set. Okay, and here is the Poisson version of. Okay, it's already a first version of the Schramm-Steif inequality, which has the following. So suppose we have given a number k, natural number k, and the square integral function u, so that I can form the multivariate Wiener-Ito integral. And I condition on the configuration within the stopping set. Recall the picture I've drawn before. I take the square of this conditional expectation, and I take the expectation of this. This thing can be bounded from above by the following expression. There's a k factorial, no surprise. This comes from the Wiener-Ito integrals. Then we have the square of the u function, also no surprise. But what is new here, and which comes from the fact that I forgot to say something here. I should say that I'm sorry for this, but I can correct this. At the moment, it's not so clear what the role of the set here is. but the role of the set is explained by the fact that I think no, it's general. I'm sorry, it's just a general stopping set, as explained on the previous slide, and then we have this property of the expectation of a conditional expectation. It is bounded from above by this expression, and you see here the probability that the set formed by the points x1 up to xk intersects the stopping set. So there is at least one point from the x1 up to xk which belongs to set. And the theorem remains true for randomized stopping sets. I don't explain this in detail, but you can think of an additional random variable which is independent of the Poisson process. And given this random variable, you have a stopping set determining, you have a stopping set, then you have a randomized stopping set. So it can also be interpreted as a random stopping set, if you like. So maybe it's better to go to this corollary here. Namely, now we have really a function f, which is determined by a randomized stopping set. And here you see the chaos expansion. So any square integrable function, well, let's assume that f is square integrable with respect to the distribution of the Poisson process, can be written as the orthogonal sum of these multivariate Wiener Ito integrals for some kernel functions uk. And assume now really that f is determined by a randomized stopping set. And that's actually the Schramm-Steif inequality for the Poisson process, which says that the squared norm, L2 norm of this Wiener Ito integral can be bounded from above by k times a quantity delta, which I'm going to explain in a second, times the squared norm, L2 norm of f of eta. And what is this quantity delta of z? It is the supremum over the probabilities that x is actually covered by the stopping set. And in computer science, and for instance, this probability is also called as a revealment property. This has something to do with the fact that the stopping set is often constructed or is a result of a certain algorithm. And then this probability tells us, this is the probability that a certain point in the state space is actually covered by the algorithm. And this theorem is really completely analogous to a theorem 1.8 in this wonderful Annals of Math paper, which is formulated on the discrete finite hypercube using Fourier-Walsh expansion. And what we are using here instead are the Wiener Ito integrals, which are playing exactly the same role as the Fourier-Walsh coefficients, or the Fourier-Walsh expansion. Okay, so now what can we do with this inequality, and what have actually Ode Schramm and Jeff Steif done with this inequality? They have done wonderful things. I cannot say much on the proof. It's just we are using the Markov property of stopping sets, of course, and we are applying actually the chaos expansion to conditional expectations. So it's a little bit tricky, but basically it's the same idea as in this Schramm-Steif paper. Can I ask, do you have a question? Because I cannot hear anything and I cannot see anything except my own screen. Herr Götze, ich bin noch zu verstehen, ne?
Wunderbar.
Okay, weil ich bin, Entschuldige, sorry, I'm a little bit nervous for some reasons. Okay, thank you very much. Okay, so what's the time? Yeah, it's fine. So let's try to do something with this inequality. By the way, let's proceed. So I would like to touch on two topics, namely noise sensitivity and also exceptional times. I haven't announced exceptional times in my abstract, so maybe I will treat this very, very briefly. But I mentioned noise sensitivity. So what's noise sensitivity? This is a concept which was introduced in another paper by Audit with two co-authors. And I would like to explain it in the context of a Poisson process. So what we are going to do is to look at the free birth and death process as a stochastic process taking values in this set of configurations with marginal distribution p lambda. So for any t, the distribution of eta upper index t is that of a Poisson process. And it's a free birth and death process, which means that points die independently of each other. And there are, at the same time, we have a birth process going on, both is independent. So I don't think I need to explain this here. So it's a free and birth death process. It's a Markov process, very nice. And for small t, for large t, eta t is getting more and more independent from eta naught. So the eta t is forgetting eta naught to initial configuration. But for small t, eta t is still very similar to eta naught and can in fact be interpreted as a perturbation. We have a certain thinning going on, and then we are adding independently another Poisson process, so that in the sum, the overall effect is just the intensity measure stays the same. And I would like to mention here that if f is given by its chaos expansion, then the conditional expectation of f applied to eta t, given the initial configuration, is given by this formula. And some of you will recognize, oh, okay, that's the Ornstein-Uhlenbeck semigroup when considered as the function of the original initial value eta. So in a sense, a free birth and death process is a probabilistic pathwise Markovian representation of the Ornstein-Uhlenbeck semigroup. Okay, and here's now a nice definition coming from this other paper I've mentioned, which was and still is extremely influential, Benjamini, Carlyle, Schramm, which is introducing noise sensitivity, and noise sensitivity is an asymptotic notion. So what we have here is a sequence of measurable mappings on our space of configurations. So we don't change this. Square integrable with respect to the distribution of a Poisson process. And it's called noise sensitive if this relation holds for one positive t, or for all, which is equivalent. So let's think of t as some small epsilon parameter. And then we see here, that's the covariance, because eta t has the same distribution as eta. So this is really the covariance between fn of eta and fn eta t. And if it goes to 0 as n is getting large, then we call this sequence noise sensitive. So in particular, in many applications, fn is actually Boolean. So it takes just the value 0 and 1, and that this is just really asymptotic independence. So somehow, the knowledge of eta t doesn't help you in order to get knowledge on eta. It's noise sensitive. So this, yeah. So that's this wonderful definition of Benjamini, Carlyle, Schramm. And it's not just a definition. They have observed interesting things, and we try to transfer some of these things to the Poisson setting. So there are some equivalent ways to characterize noise sensitivity. In the case where the squared, where the L2 norm of these random variables is uniformly bounded in N, namely noise sensitivity occurs if and only if for any, it is expressed in terms of the chaos expansion, and if if the norms of these kernel functions go to 0 for any k, then the sequence Fn is noise sensitive. So one could call this only high frequency measures. So you can sum here over k up to 1 million or even higher. So just sum up all the first terms of the chaos expansion, it goes to 0. The squared norm goes to, the norm goes to 0. And it's not hard to see that it is true just by this relation here, namely if we put this square of the expectation on the other side, then we get on the left-hand side the covariance, of course, and that's given by this infinite series, and that's immediate from the Ornstein-Uhlenbeck representation here. If you multiply this term with f of eta and you take the expectation and use the orthogonality properties of the Wiener Ito integrals, you have this formula. And once you have this formula, then it's easy to say that this is true. And maybe another bit of information is the following, which is also maybe helpful, namely this covariance here goes to 0. That's a typo. T is fixed and n should go to infinity, I think. Okay, let's correct this. Okay, this must be n. Maybe it's even in our paper. So it means that asymptotically, if n is going to infinity, the knowledge of eta really doesn't help. It's just getting asymptotically independent in this sense. Okay. And now we can actually use the Schramm-Steif equation to actually characterize noise sensitivity in an abstract way, namely given a sequence Fn of measurable mappings as before, uniformly with the squared norm, with the norm uniformly bounded, then we can say the following. If we have for each n a randomized stopping set, Zn, which is, first of all, determining Fn, and that's also missing here, determining Fn, okay, such that the revealment probabilities, these revealment probabilities go to 0 uniformly in X, then Fn is noise sensitive. And given the Schramm-Steif inequality, our Poisson version, that's actually not so hard to prove. Because randomized stopping sets, let's go back just for a second, occur in this inequality here. And what you have to do is you have to use the fact that the function Fn is actually determined by the restriction of eta to z, and you have at a certain stage to apply Cauchy-Schwarz. Okay. And actually, we can give a more detailed result because the Schramm-Steif inequality is an explicit bound. It's you have the delta n on the right-hand side, and you can actually give an explicit upper bound for the covariance between Fn of eta and Fn of the perturbed eta. The e to the minus t doesn't matter here, but this is good here because it's 1 minus e to the minus t, and if t goes to 0, this goes to 0 here, which is good. Good news. Okay, maybe I skipped the exceptional times. I'm sorry. I haven't mentioned them in the abstract anyway, so you can ask me in the discussion part. Exceptional times, I skip it, even though it's interesting. And let me spend the final part of the talk to discuss a certain application, namely k-percolation. I first need to define what k-percolation is. It's a continuum percolation model. It's a generalization of the Boolean percolation model. So we are in the Euclidean space Rd, and we consider the space, let's say, calligraphic Kr of non-empty compact subsets of the d-dimensional Euclidean ball. So we basically look at uniformly bounded compact subsets of Rd. Then we take a probability measure Q on this space with a small regularity assumption. So the probability that that such a random K contains a small ball must be positive. And now what is our Poisson process? Our Poisson process is now living on the space Rd. Rd is modeling the centers of grains, and times Kr, which is modeling the space of shapes. And here's the intensity measure, and the intensity measure is the multiple of a product measure, and the multiple is the intensity, of course, and it's called gamma. So in the classical Boolean model, we just take the union of all the grains, where a grain is given by the location, by the grain shifted to the location. Okay. So, but here we generalize this a bit, namely we say that O is the random set of all points which are covered by at least k grains from eta. It's a special case of an excursion set, by the way. And it can be motivated by algebraic topology, as Yogesh pointed out quite some time ago. But if you are not feeling comfortable with an arbitrary k, just think of k equal to 1, and then O is really the classical Boolean model. Here are some percolation definitions. You might have seen them yesterday, I don't know, because I had to miss yesterday's talks. I'm very sorry about that. So theta of gamma is a standard notation. It's the probability that the origin is actually part of an infinite cluster. So that's the notation here. An infinite cluster is formed with respect to this calligraphic O set, points which are covered at least by k grains. Okay. So theta s of gamma is the probability that the origin is connected to the boundary of an Euclidean ball with radius s, or centered at the origin. And here's the critical gamma. It's the smallest gamma such that this theta of gamma becomes positive. And it can be shown because we have uniformly bounded grains that there's a non-trivial phase transition actually. So gamma c is positive and finite. And here's an example of a noise-sensitive sequence of functions. So assume that we would like to understand the behavior of the system at criticality. So we assume that the Boolean model is at criticality. The criticality refers to k-percolation. Okay. So we take the critical parameter and we take a rectangle of this form. Let's say kappa is equal to 1, it could be 2, or could be 3. And I don't define horizontal crossings explicitly. I just draw a picture in the case k equal to d equal to 2. So you have a rectangle, and we are interested in horizontal crossings of this rectangle. And a Fn is just an indicator of such a crossing. So the randomness is really coming from this marked Poisson process. And we assume that these crossing probabilities are non-degenerate, and the definition of non-degenerate is missing. Okay, then I need to, I'm sorry for this. Degenerate means the following. So there exists a gamma naught, let's say, between 0 and 1, such that the probability of, or the expectation, actually Fn is an indicator, so I can write expectation of Fn of eta is smaller than 1 minus gamma naught and bigger than gamma naught for all n. So the probability of such a crossing should stay away from 0 and of 1. Okay, and I will discuss this in a minute. So if we assume these crossing probabilities to have this property, and if we assume that actually there's no percolation at criticality, it's an assumption. People believe in these assumptions, but it's an assumption at the moment. Then Fn is actually noise sensitive. And the trick or the key to this of the proof is to construct a suitable stopping set, randomized stopping set, which small revealment probabilities. So I cannot talk about this, but what I can do is to comment on this before concluding the talk. Namely, first of all, I said, I already mentioned that people believe in these two assumptions on these crossing probabilities. But second, in 2 dimensions, we know much more about such percolation models. In particular, I refer here to this PTRF paper, where you can see that the assumptions are actually satisfied in great generality in 2 dimensions. And so this is written in this corollary. In the planar model, we can actually conclude noise sensitivity of these crossing events. So here are a few references. So in particular, I would like to, yeah, this is really a nice book here. Gaban and Steif, you find a lot of information on noise sensitivity of Boolean functions. And for this talk, this wonderful paper, sorry, was essential. Okay, so I think that's all what I wanted to tell you. And thank you very much for your attention. I'm ready to take questions.
Okay. So thank you.